NVIDIA Jetson Nano is a very small but powerful AI computer at a very economical price of $99. It is also very power efficient as it only requires 5 watts to operate. It can be used in a lot of applications such as speech processing, image classification, and object detection. The NVIDIA Jetpack SKD is the AI platform used for developing software or any other integration needs. The device can support a network of sensors to process large neural networks. It also has access to multiple input-outputs, memory, clock, power management, and a lot of other hardware, software implementations. Here are some general specifications of the device. The GPU utilizes an NVIDIA Maxwell architecture with 128 NVIDIA CUDA core. The CPU uses a quad-core ARM Cortex A57MP core processor. There's 4 gigabytes of memory with 64-bit LPDDR4, 1600 megahertz, and 25.6 gigabytes a second. There's 16 gigabytes of storage with a 5.1 flash. There's a video encoder that runs on a speed of 250 megapixels a second, and a video decoder that runs with a 500 megapixels per second. There's also a camera with 12 frames MIPI that runs at 18 gigabytes a second. Here's a continuation of the specifications. For connectivity, if Wi-Fi is needed, the device needs an external chip to be able to connect. It can also connect via Ethernet cable. For the display, we have an HDMI 2.0 or a DP 1.2, an eDP 1.4, or a DSI. The UFI uses 4 USBs, one of which is 3.0 and the other 3 are 2.0. For input outputs, we have 1 SDIO, 2 SPIs, 4 I2Cs, 2 I2Ss, and a GPIO. The size of the device is 69.6 millimeters by 45 millimeters. It also has a 260 pin edge connector. Continuing on the general specifications, we move into more of the hardware of the device. There's a 40-pin expansion header used to connect the device to the outside world. To power the device, we have a micro USB power supply connector that supplies a voltage of 5 volts and 2 amps. We have Gigabyte Ethernet, 4 Type A USB 3 ports, and HDMI and DP display connectors. There is also a barrel jack that will supply up to 4 amps if we need more than the 2 amp power supply from the micro USB connector. There's a camera connector that supports IMX219 camera modules. This can be an external Raspberry Pi camera module or any other external cameras can be connected to the computer. We also have an 8-pin button header used to control the system's power and reset signals. There is a 3.3 volt serial port header, which allows access to the UART console. A PoE header helps to verify the DC voltage on the Ethernet connector. There's an M2 key E connector, which is used for wireless connectivity. Below the device is a micro SD card slot located under the board. There's also a passive heatsink that supports a 10-watt power budget and 25 degrees Celsius ambient temperature.
The Jetson Nano's GPU is a 128-core Maxwell architecture GPU. The Maxwell architecture runs at 921 megahertz, and is the next generation architecture for CUDA computing applications. It utilizes an improved streaming multiprocessor, which allows for better energy efficiency, logic portioning, workload balancing, clock gating granularity, and compiler-based scheduling. It also allows for a larger number of instructions issued per clock cycle. The SMM, or Streaming Multiprocessor Maxwell, quadrant-based design is 4 32-core processing blocks. Each SMM provides 8 texture units, 1 polymorph engine, a dedicated register file, and shared memory. Hi, this is Reese Dietrich. The significance of the GPU in the Jetson Nano is that it is good for AI and machine learning capabilities. GPUs are well suited for these applications because, unlike CPUs, GPU architecture focuses on parallelism. The number of cores are significant in computing because they allow for simultaneous operations of tasks. There are 128 cores. GPUs have many more cores when compared to CPUs because this is important for specific tasks such as graphical rendering. For this reason, GPUs are extremely important when used in gaming or video editing software. In video editing and gaming, these cores are useful for simulating different particles like smoke and fire, or physics objects like destruction of a building or liquids like water. It's also important in AI and machine learning because you can run a lot of simultaneous simulations and tests all at once. The CPU is a quad-core ARM A57. It runs at 1.42 gigahertz, which when compared to a desktop processor is kind of slow. It's still pretty fast for a board of this size. The small form processor is well suited for the focus of the NVIDIA Jetson Nano. Since most of the heavy lifting is accomplished by the GPU, the processor doesn't really need to be quite as powerful. When compared to the Raspberry Pi 4, the processor is slightly outdated. It could maybe use an upgrade as it's a little slower and less energy efficient, but the processor is still more powerful than what can be found on the Pi 3. Upgrading the CPU would likely increase the cost, and it's only $100, which is already really inexpensive. In the case of the hardware on the Nano, you might think that it's too weak to accomplish anything too interesting. But when it comes to the real-world usage of the CPU and GPU, the Nintendo Switch utilizes similar hardware to the Jetson Nano. In fact, it shares the same GPU, but a slightly more powerful CPU. The CPU in the Nintendo Switch is an older A53-based model, as opposed to the newer A57 in the Nano. However, it utilizes 8 cores instead of 4. This shows that when properly optimized, the Jetson Nano is quite powerful for its small size. This is apparent if you've ever played any games on the Nintendo Switch. Nintendo is often known for having slightly lower powered hardware, but they still manage to run some impressive games on it. The Jetson Nano utilizes 4 gigabytes of LPDDR4 RAM, which is fairly standard in today's world of computing. However, this RAM is not customizable like the Raspberry Pi 4, where you can order it in a 1 gigabyte, 2 gigabyte, or 4 gigabyte memory size. Since the RAM isn't customizable, it's probably because 4 gigabytes is the minimum requirement for this board. Increasing it would likely also increase the price. Another reason you wouldn't really want to go below 4 gigabytes is because these 4 gigabytes are shared by the GPU and CPU, unlike a PC where the GPU has its own dedicated VRAM. Because of the importance of RAM and usually wanting as much as possible, it could be argued that 4 gigabytes is not quite enough. The Jetson Nano uses a micro SD for its main storage. It can be any amount that a user can pick from, however, it does need at least a minimum of 16 gigabytes. SD cards are useful because they have fast access times to files, but they do suffer in read-write times when compared to SSDs and HDDs. They also have slightly higher failure rates than SSDs and HDDs. The obvious benefit to using a micro SD as the main storage device on the Jetson Nano is that it is extremely small and helps reduce the size of the board and its power requirements. There is an involved method to move the root of the Jetson from an SD to a USB SSD to increase performance and load times by up to 4 times the original speed. In some applications, booting from an SSD could be very helpful because SSDs generally boot computers extremely fast.
The Jetson Nano features 4 USB 3 ports and a micro USB 2 port. These ports are standard in modern computing, and the use of 4 3 ports allows for better data transfer between peripherals when compared to the Raspberry Pi's 2 port USB and USB 2 ports. This is also beneficial from experience of the time I used a Raspberry Pi Zero and it only had one USB port. So when we were using it, I had an issue where until we set up a remote desktop, that if we needed we couldn't use a mouse and keyboard at the same time. We had to unplug the mouse to use the keyboard and unplug the keyboard to use the mouse, and it was very inefficient. So the number of ports that the Jetson offers is very beneficial to the user. Display for the Jetson Nano is fairly straightforward. Utilizing any standard HDMI port, it is easy to find cables that connect to almost every modern display. Compared to the Pi 4, which uses a micro HDMI, the usage of the standard HDMI is much more convenient. GPIO, or General Purpose Input and Output. As with many boards of this nature, the Jetson Nano has 40 GPIO pins, allowing it to support plenty of peripherals. This includes anything that may use UART, SPI, S2S, or I2C. 40 GPIOs is standard in applications such as these. The Raspberry Pi also has 40 GPIO pins, and while not SoC, system on a chip, or microcomputer, an Adreno Uno has 20 GPIO, and the Adreno Mega has 54. A major feature that seems to be lacking is the ability to use wireless internet on the Jetson Nano. It is only equipped with an Ether port out of the box, unlike the Raspberry Pi 4. This means it requires a small USB adapter or similar device to connect to wireless internet. So currently, out of the box, the device has no Wi-Fi internet access or Bluetooth ability. Video capabilities of the Jetson Nano, starting with encoding capabilities, offers 250 megapixels a second with an option of 4K resolution 30 frames per second, and 1080p options at both 30 and 60 frames a second. When it comes to decoding capabilities, though, it offers 500 megapixels with options of 4K at 30 and 60 frames a second and 1080p at both 30 and 60 frames a second.
Hello, my name is Matthew Taylor. Today I'll be going over the challenges and opportunities associated with the NVIDIA Jetson Nano development kit. So with the setup of a particular AI, there are many factors that go into the efficiency of it and the general workflow or how the data is processed throughout the entire system. So some of these factors include how the model is set up, how big the data it's going to be processing is, the amount of calculations, the amount of adjustments for loss or accuracy, a lot of different factors that can be included in how differently these different systems are processed. So we can see that many calculations need to be done, so a lot of hardware is required, whether it be locally through cloud computing with multiple computers or systems. Generally, you're just going to be required a lot of CPU or a lot of GPU power to be able to make the number of calculations that are required. In today's world of the Internet of Things, this is one of AI's most challenging problems, prohibiting the efficient use of this technology on a large scale. Because of the large amount of hardware required, local machines or cloud computing services can be required in different AI implementations. This can be a challenge for AI implementations, especially in the Internet of Fields range with the many devices used and connected to the network. This can be a challenge, especially for those in low signal areas or for larger projects, which may consume a lot of bandwidth or space with a local machine.
With the use of the NVIDIA Jetson Nano, AI could be implemented in exponentially more situations, helping improve everyday processes in the home or business. Some of these benefits of using this board include it's rated for 5 to 10 years of life in a production environment, so that's very impressive considering its price and its size. Board is slightly larger than a credit card, so going off of its size, very small, very modular, can be fit in a lot of areas, and can process a lot of data just on that small card. Another benefit is in-house processing, no cloud computing needed, so another great benefit can always overlooked. Being able to process everything in home and not have to use any outside resources, sending bandwidth, or paying for any memberships for cloud computing, you avoid a lot of that by using this board. So a lot of cool benefits in using it as well. Next, I'd like to go over some resources to learn more about embedded development and specifically AI development in these embedded boards. The first one I'd like to go over is going to be CAP 4613. It's Intro to Deep Learning. It's actually an elective course taught at FAU focusing on deep learning methods and theory with practical assignments using different libraries in Python. I actually took this course last semester and really enjoyed it, learned some really cool things about machine learning and deep learning, and actually got to do some applications in Python, including different models and different designs of those models. So that was pretty cool. Next, I'll go over embedded computing. It's a section on NVIDIA's website, or specifically their developer section. So NVIDIA provides great machine learning resources for various Internet of Things devices, including the Isaac SDK for AI-powered robot development and DeepStream SDK for video streaming analytics. So those are just a number of SDKs they have available to let you go ahead and actually make your own developments, different designs using those SDKs. Isaac would be pretty cool to do any kind of robot development, so they provide all the resources and libraries for that. And deep streaming being any kind of video incoming, CCTV, any video recording, really anything you can pick up any analytics from. They provide the resources and libraries for that as well. Another resource I'd like to go over is going to be TensorFlow Lite. It's an open source deep learning framework for Internet of Things devices developed by Google. Some services that use this framework include the Google Assistant, Shazam, to name a few. There's a really cool service that allows you to use Google's deep learning framework. They have different building blocks for the models. They allow you to add individual layers. You can pretty much fully customize different models, neural networks, a lot of cool deep learning technologies inside of that framework as well. Mostly used for like app development. Actually a slimmed down version of the TensorFlow library. It's the full library offered by Google. Really just slimmed down for any mobile application or in this case embedded application as well.
Hello, this is Nazik and I will be presenting a tutorial on getting started with deep learning on NVIDIA Jetson Nano. The tutorial consists of 6 parts. The first is meeting all prerequisites and requirements, then setting up Jetpack SDK, then building and compiling the project, and then using deep learning models to classify objects in images and locate objects in static images and real-time video streams. The Jetson Nano uses a micro SD card as a boot device, so one of the prerequisites is to burn a boot image onto a micro SD card. There are a few power supply options. The first option, which the board is configured to use by default, is the micro USB power supply. The second option is to use a power jack. And the third option is to use an expansion port. In order to set up the development environment, the board needs a connection to the internet. One of the options is to use the Ethernet port that comes on the board, or another option is to expand the board using a wireless networking adapter, which will enable the board to connect to a Wi-Fi network. In order to write image to the micro SD card, first we'll need to download SD card image from NVIDIA and then use Etcher to burn the image to the SD card. Next, we'll need to connect the board to a monitor, a keyboard, and a mouse. Then plug the power supply. Once the board is powered, it will start and boot into Linux. The user will then be asked to accept Ubuntu conditions and to set up a user profile. A user profile includes name, last name, and password, and a few other settings. Once the user profile is set up and all conditions are accepted, the board is all ready for development. The next step is to set up Jetpack SDK. So let's start with what is Jetpack SDK. NVIDIA Jetpack is a software development kit made specifically for Jetson board. It contains most of the components and libraries required for development of deep learning and AI applications. Some of the components include OpenCV, CUDA, and TensorRT. For users' convenience, a SD card image that we burned earlier comes pre-populated with the Jetpack components, so we won't need to install anything. The next step is to build and compile the project. In this step, we will be building Jetson Inference. Let's start by defining what is Jetson Inference. Jetson Inference is a real-time deep neural network vision library for NVIDIA Jetson. The library uses NVIDIA TensorRT for deploying neural networks onto the Jetson platform and improving computational performance and power efficiency using graph optimizations and kernel fusion. And basically it contains all of the scripts that we will be using for classifying objects and detecting objects in real-time video streams. In order to build the project, we'll first need to clone the repository. For that, we'll need to run these commands in the terminal. We'll first git clone the repository, change the directory into Jetson Inference, and update all submodules. By default, it only creates bindings for Python 2, so we'll also need to run this command. Once it finishes installing Python 3, we need to configure the build using CMake. For that, we'll make a directory build, change directory into build, and run CMake. During the build process, there will be several points where the user will be asked for an input. The first such point is the selection of models to download. By default, it downloads ResNet 18 and GoogleNet. You can skip this process by clicking enter, because later you'll be able to run download model script to download additional models. The second such point is installing PyTorch. The script will ask for a version of PyTorch to install. Again, you can just click enter and change that later using install PyTorch script. Once the build is complete, we'll need to compile the project. For that, we'll need to stay in the build directory and run these commands in the terminal. Make will compile the project. It may take some time, so be patient. And once it is complete, we'll need to run sudo make install and sudo lt-config, which won't take long. The project will be compiled into Jetson inference build arc64 directory, and this is the resulting hierarchy of files. We will be mainly working with the bin directory where all the sample binaries are built into. And now we're finally ready to start classifying static images with ImageNet. In order to use a console program to classify an orange, we'll first need to navigate into Jetson inference build arc64 bin directory. There we'll need to run a C++ program, ImageNet console, with parameters of network and a source image. This repository comes with some test images, and we'll be using an image of an orange. And here's shown a sample output for a green apple, which is predicted to be 100% Granny Smith. ImageNet console accepts 3 command line arguments. The first is the path to an input image, optional path to the output image, and optional network flag. Here's the list of networks available. We previously downloaded only GoogleNet and ResNet 18. Additional networks can be downloaded using a download net models script. Let's try to classify an image from Google to make sure that we are using an image that the model has never seen. I searched for a jellyfish and used the first image found. ResNet resulted in 98.68% of probability of it being jellyfish, and GoogleNet resulted in 100% probability. The next part of this tutorial is locating objects in static images using DetectNet. We'll be using a console program, DetectNet console, with parameters of network and the source image and the output image. For example, this image resulted in these bounding boxes, predicting that each of these objects are a person, which they are. This program comes with many options to customize the resulting image. And these are all the arguments that are accepted by this program. As in previous part, let's try to test it on Google Images. In this case, I searched for cars and used the first image found to predict. And it predicted with 96.6% that it is a car. Here I searched for fridge contents, and you can see that it recognized the refrigerator and 4 bottles on the upper right corner. Here's an image of people and animals with a person and a dog predicted successfully. There are many pre-trained models available which can be downloaded using a download model script. The next part is locating objects in a real-time video stream with DetectNet. Running the live camera detection demo is very similar to static object detection. The only difference is that it requires a video stream input. Conveniently, a Raspberry Pi camera also works on Jetson. The Jetson Nano comes with the same connector as a Raspberry Pi does. In order to run real-time object detection, we'll first need to navigate into the same bin directory and run DetectNet camera program. Jetson Nano comes with 2 camera interfaces available, so we'll need to specify which camera we want to use. In this case, for a Raspberry Pi connector, the option is 0. Here you can see some of the screenshots of objects detected in a video stream. You can see a cup, a book, a person's hand, and a laptop. Here you can see some additional objects detected in a video stream. A dining table, a car. You can also see an example output in a terminal of detecting an object.